Okay, so continuing our example, when I multiplied this, I forgot to apply it to this first term here, so this is actually going to be x naught right here. So x naught, okay? So I just want to keep that in mind, and this is going to be from x naught to x, okay? So, I will need another page here. I'll be right back for that. Okay, let me go ahead and write this on the next page. So we have t is equal to my constant, which I'm going to go ahead and write out. It's going to be 1 over square root 2e over m, and then an x naught as well. So square root of that. Now we have the integral that we just took here. So that'll be 2 times, or divided by, actually no, times x naught plus x square root. So this is from x naught to x. Okay. So from that we'll get, I'm going to go ahead and pull all of this out so it looks a little bit nicer. So we have 2 times mx naught over 2e square root. And then we'll have x naught plus x 1/2 minus x naught plus x naught 1/2. So just looking at this portion, we're going to get x naught plus x 1/2 minus 2x naught 1/2. Okay. 2 mx naught for 2e. Okay, and we want to solve for x. So this might get a bit tricky. Let's see. We will have t times this constant here. Times 1/2 equals x naught plus x to the 1/2 minus 2 x naught 1/2. We can add this term over, and I'll need another page. Give me just a moment. Okay, so when I was adding another page to work with, I noticed a few things going on here in my work. So I just wanted to go over a few things. So the way that the textbook gave us this example, that the potential energy is equal to minus E x over x naught, gives me these values of x naught plus x, as we saw here, this positive value, since in this equation we have E minus U, right? And when I was looking at what they were doing, they somehow got that this was a negative value here still. So I'm thinking the only way that this problem will be a little simpler than how I'm doing it right now is that if our u here was positive instead of negative. Okay, so we're going to say let this be positive instead. Okay, so that means a few things. That means this is going to be positive here, which makes this piece negative, this piece negative, this piece negative. I also noticed when I took the derivative, I forgot to carry in that negative outside. Okay, so we have a negative there, so a negative here, and negative here, and here. This is still minus. Okay, so that kind of catches us up to where I was solving for our time here. So let's go ahead and erase a few things. So if x naught minus x naught, that's going to give me 0. So I'm going to erase. Uh-oh. Oh, I can't erase it. That's right, because I went out of it. Let's see. Let me, I guess, mark it off. It's the best way we can do it right now. Okay, and same thing here. Okay, so this makes the problem a lot simpler than it was. Okay, so now we have t times all of that constant stuff out front is equal to negative x naught minus x. Okay, so we're going to take that and continue on the next slide. So now we have, I'm going to say minus t, yeah, times 2e over m x naught, and that was in a square root, times 1/2 equals x naught minus x, and that was square rooted. Okay, so this is our form we have. And so if we want to solve for x, we need to go ahead and square both sides. So let's do that. So we get t squared times 2e over m x naught times 2 squared, that's going to be 1/4, and that will equal x naught minus x. So then what we'll do is we'll solve for x. That will give us x of t. Okay, so it'll be x as a function of t. So we'll go ahead and say that this is now x naught minus e over 2m x naught t squared. Okay, so this is our function in terms of time, our position function in terms of time. Okay, and I believe that is what we're looking for, position as a function of time. Yep. Okay, so that made it a lot easier. I do think maybe there was a typo in the problem itself, okay, because this equation is correct. Okay. All right, so let's go ahead and move on to potential energy diagrams. These are a couple of examples I wanted to show you. So we have this one, which is an object in free fall. Okay, so we've got energy versus the height above ground. And with this, we can go ahead and plot our potential energy, which we have defined as mgy when we're talking about gravitational potential energy. Okay, so this would be gravitational potential energy. Okay, and so this makes sense that this line is linear since it just depends on y and mg, which are constants. Okay, now we can look at another one. This is a glider between springs on an air track. So this is what we're talking about. If we were in class, I could probably bring one of these out and show you guys what I'm talking about. But we have an air track, and a glider that just will glide along. Think about like a, oh, what's it called? The hockey tables or the hockey puck tables that you play like in an arcade. I cannot think of the word right now. But that's what the air track is. It's pushing air so that you're essentially frictionless, okay? And in this case, we have a glider that's connected to 2 springs, and so it'll just kind of wiggle back and forth, okay? And this is the potential energy diagram representing that motion. So in the middle, where we don't have any motion, this is the equilibrium point, okay? So that would be like here. And then if we pulled it one way, then we'd have where we have the highest kinetic energy, okay? Or we have the highest energy. And then as I let it go, it'll go all the way back to the other spring, and we'll have another turning point here, okay? And where we'll have kinetic energy again. So this is the motion of something connected by 2 springs, okay? And in this case, we have a glider on that air track. Okay, so again, the energy versus displacement, okay? So this shows you the how the energy, I guess, is distributed throughout that motion, okay? And again, we note that our potential energy here is equal to 1/2 kx squared, since it's spring potential energy, okay? And so these are going to be that slope here, that x squared, not slope, I'm sorry, the graph equation, okay? All right, so we can go ahead and do an example real quick. Find x of t for a particle moving with a constant mechanical energy and a potential energy, u of x is equal to 1/2 kx squared, where the particle starts from rest at time t equals 0. So we want to find some kind of equation to describe that motion, just like we did before. Okay, so let's see. We have a constant mechanical energy, and we have some potential energy. So we can say t is equal to the integral from x naught to x dx over, let me go back and make sure I've got this right. 2e minus u of x over m, and that is in a square root. Okay, so we can go ahead and plug in our value here. 2e minus 1/2 k x squared over m, all in the square root. Okay. Give me just a moment. All right, so I'm going to go ahead and rewrite this a little bit. So I'm going to say the integral dx, and I'm going to pull this out from this term. So what I'll do is I'll distribute this 2 to get rid of the 1/2. So I'll have e, 2e, okay, and then I will divide by k throughout. So I'll have k minus x squared. Okay, so that's that, and then over m, and then inside of a square root. Okay. So from here, you will need to use some kind of special integral form to solve this, and so we'll do that in the next video.